Hello everyone, today we are going to talk about what is an important bugs in the deep learning library. So first, in order to understand what is bugs in the deep learning library, first and foremost question would be what is a deep learning library? So a deep learning library provides us with the tools that enable us to develop, train, and optimize, and then do the infer of deep learning models to do, and it also provides something other like traditional machine learning tools. It would also have some integration of numerical computation graph. So basically, deep learning library contains two systems. The first system would be providing math calculation. It would start from the basic mathematical operation like add, minus, negative, convolution, pull, and it also contains some of the tensor-related control related operation like reshape permutation, random, those are very important for the computation. And based on the basic math operators, there would be automatic differentiation, which would have some automatic uh, autodiff mechanism like backward propagation, and it would also enable calculation across different devices, such like with TensorFlow you can enable uh, use your phone to do the text to speech transformation, and it also use several others. It also integrates several other numerical libraries and devices. For example, it can use XLA and OpenMP to parallelize and optimize your code, and it can also use the GPU and the driver to accelerate your computation. Uh, an important foundation optimization is that it would uh, break down a very complex formula, a very complex computational graph that's composed by those operators with its arguments into some basic math operations, basic nodes, and then it can reorder and fusion those operations together and to get a more optimized and efficient result. It uh, in the second system, it also provides a higher abstraction of uh, deep learning training and other things like it provides a higher abstraction for networks like it gives you the popular optimizer like SGD and Atom. It also enables you to do the gradient clipping. You also can do something like um, Dropouts, Batchnom, or something like that. It also contains a lot of helper functions for the deep learning, such as data loader with some operations to the dataset, and they will have their own performance estimator and visualizer. So we need to introduce you with three most popular deep learning libraries. They are PyTorch, TensorFlow, and GX. So first is PyTorch. This is the most successful deep learning library that's used in the academic world. So basically, almost 90% of the papers are using PyTorch. Why? It is because PyTorch is much more Python centric. It enables the eager execution. So once you type in an operation, it instantly gives you the result back. So it's much more easier to debug. So it is based on the dynamic computational graph, but it It is sponsored by Meta and integrated with Fast AI and Hugging Face like this. But nowadays, because after you develop the model, you also need to prune the model and to optimize the model to shrink the size of the parameters and to optimize it. But in the eager execution context, it will be hard to do that. So PyTorch also released Torch Dynamo and Torch Inducer that would catch uh, the mass operation from the Python and then replay it. Oh, it's not. It's directly catch them from the code. Okay. Uh, but it is like a mixture. It is a intermediate solution of the dynamic computational graph. And TensorFlow, on the other hand, uh, is a typical one for the static computational graph. It is run in the graph mode, which means they will do the most logic at least in the early age of TensorFlow. They will do implemented most of the logic in C and C++. And then they will have Python as the interface. And uh, once users write all the model, it will uh, translate those Python back into the C API and then into the computational graph, and then it will optimize on that computational graph to give a much more efficient selection, and which is natural for the distributed training because you need to decide which tensor are put into which devices, which machine, and to enable the max to make the training able to do and makes the training faster. And TensorFlow is sponsored by Google Brain, and TensorFlow also has its own model publication platform named TensorFlow Hub. It is much more production focused, but due to the popularity of PyTorch, TensorFlow also released TensorFlow, the second version, which is TensorFlow Eager. TensorFlow Eager enables eager execution, of course. And the third one, that why I need to introduce its GX, is it's a much more lightweighted auto-differentiation numerical calculation library. It is also Python centric, but and the research focus just like PyTorch, but much more lightweighted, and it is also sponsored by Google Brain, and is another uh, high point of the highlight of the Google Brain. Uh, that they spend a lot of manpower on it. That's why I introduce it. After that, we need to understand what would the general bug situation in those deep learning library. So here I choose to use the data from this paper. Uh, Empirical study of bugs inside PyTorch, a replication study. That is because it is published last year on 20 and 23 on ICSME, which is a relatively new research, and it is relatively comprehensive. So as we can see that here the on the left side is the main type of those bug. On the right side is the uh, most influential phenomenon, the symptom of those bugs. And we can say that the most important bug, except for logic error and algorithm implementation wrong, would be inconsistency between APIs and and we can also see that the transformation on the tensors like type confusion and dimension mismatch and reference type error is also very important in the deep learning library. So this picture is for the PyTorch. And we can see that only the logic error, why all different kind of bugs can produce performance degradation, which means memory out of chunk or the memory out of order or the time is too slow. All of the bugs can do it can make the performance worse, but only the logic error can contribute to harm because that is makes sense because only logic error can write something as loop. So another thing would be a comparison between PyTorch and uh, TensorFlow on the distribution of bugs of the types of the bugs. So we can see that the blue one is PyTorch and the yellow one is TensorFlow. Because they are operated in different community cooperation way and they have different kind of community, we can see that instead PyTorch has a much more rate on the wrong algorithm implementation and API inconsistency and logic error, but um, TensorFlow has a much more processing error, which means some of the argument isn't correctly initialized. So TensorFlow relies on the initialize of the model very much, which makes sense. But again, both of the platform has a lot of type confusion and dimension mismatch thing. And API inconsistency is very, very severe in both of the library. So this is a symptom comparative on these two libraries, so we can see that the build failure is much more popular on TensorFlow. That is because I think TensorFlow utilize Clone to do the NVPTX transformation, but in these two different develop modes, I think TensorFlow relies on NVCC directly much more. So that's why it, it has a very complex build torching and it's much prone to have bugs on the build failure. And about performance degradation, I think PyTorch found it much more harder and fix it much more harder. I think again it's about their research community thing. And here is a comparison of repair patterns between them. We can see that the value chain, all of these are if we are going to do the automatic attachment, we can just do change a little bit of value and parameter and condition to fix a patch. So we already see that TensorGuard has done that, which makes the LLM to automatically fix bugs of deep learning libraries be able. And after that, I would describe some of the most important bugs in the last year. The first one would be CVE 2023 33976. It is only affected TensorFlow it lower or equal to 2.12 version, and the problem is very easy. It's just feed a tensor with higher rank into the upper bound operators, upper bound functions, APIs. Yeah. So where can we use this API? We can use this in histogram binning, like map RGB value into a series of labels. So instead of having three values, we now have a curved value. So here we can see that this is the triggered test case. It is very easy, but we need to mention that this bug only happened in eager mode, not graph mode. So in eager mode, it would be have directly a crash, but in the graph mode, it would throw an invalid argument error. So the impact would be only crash. So maybe it can be used by DDoS. As a patch, it would be very simple. We just add the developers just add a checker. So we can see that sometimes if even if the result is only crashed just because the API is relatively uh, benign and should be used by users, a crash can also be a CVE and be important. The second one would be also actually named GHSL 2023-181, and this one is a little bit different. It is not specific to PyTorch or any of its version. Instead, it exists on the configuration of GitHub Action file, which is actually you can directly paste a variable into the a shell command that call the peasants. So if you um, created a bench named who am I, but with a quote, so you can force the shell to evaluate who I am as branch name, and then you push it, then each action would automatically evaluate. But you also need to have the end. So it will create information disclosure. So although GitHub Actions is running on the cloud, running on the running in the Docker container, the Docker containers still can contain some of the confidential data that isn't available to the normal users. For example, some of the testing are only visible for higher rank maintainers. So the patch is very subtle. It follows the security policy of GitHub. It turns this it puts this variable into an environment and then use this environment OS environment to call to as an argument to call this Python. So I was thought if this can fix this problem, but I trained and yes, the problem was fixed. After that, this would be a bug that is not CVE, but the developers of the PyTorch is very concentrate on. That is PyTorch 124.807. It affected this PyTorch version, which is not public available until fixed this bug. So the basically the developers found this bug before merging, and the main problem is the count. It's a reference count of the private memory pool used in CUDA cache allocators isn't properly counted, so it would which is used in graph capture like this and trigger like this and which would cause first memory leak. Second, due to some of the limitation of graph replaying mechanisms, it may also have some of stack error. So we need to provide some of the background for it. So why we need private memory pool in the PyTorch? So we know that CUDA graphs allows you to capture the series of GPU options and replay it, but you need to memorize those the memory addresses that is used in that GPU in that capture, and then you need to make sure those memory addresses won't be used by other tensors because the formal graph execution has terminated. So the tens in the global caching allocators, it will think those intermediate tensors are free now and they will redistribute it into other things. But now we need to stop it from redistributing. And why we not just modifying the CUDA caching allocators? That is because we also need to custom private pool uh, for the other scenarios. That is because like NVR's reduction and GML based altogether, which is all existing in a hundred series of machines, they request the memory are aligned in a special way. For example, like align in a border align for 128 bits. So they need separate tails, they need separate APIs, not CUDA allocate. So that's why they need to design a private mempool. But the private mempool is very small. It just has uh, a series of blocks and status. And the second is the package need the some need design that the sometimes multiple graphs can share private memory pool. For example, like in this example, graph and graph 2, they share the memory pool. And in this case, it can make the user more easy to write the capture mechanism. But since the mempool will be shared, you need to have extra care. So the lifetime should be independent from the contents manager. So you need something to recommend to record whether this memory pool are able to be released. Um, and in this case, the developers propose two uh, conditions. After those two conditions are satisfied, then the pool can be released and all the tensors will be collected and into other usage. So the two conditions are first, all tensors in this pool are free and no referenced. And second, no graphs are referenced this pool. So the use count is for the second condition, that is no graphs are referenced this pool now. But during the maintaining of use count, it is wrong because it is only added by begin allocate to pool and only decreased by release pool. However, in the use memory pool in this function, the author didn't call the end the release pool. Instead, it called and allocate to pool. So in that case, the use count won't be increased, it won't be decreased, and the memory is leaked. And due to the limitation that if you run two graph replay, then those two graphs shouldn't share the memory. Then so if you forgot that and you run two graph replay simultaneously, it will trigger stack error. so it would have the phenomenon of crash. So this is a related code, and the solution is only to keep this function and remove other function and clean them. So in the end, we can see that a safe security guideline and what is important about uh, in the view of the maintainers of deep learning library maintainers um, are you are using a benign models with that the model is very similar to the model in the in the documentation and not too complex or not too harmful because on the serial the TensorFlow, especially the TensorFlow, it contains some of the control flow primate in their computational graph. You can do almost anything with only mode. And second, you shouldn't use a deep learning library in an untrusted environment or network. So in this case, if you found something in their protocols, in the network protocols of distributing learning, you better report them to some platform like Hugging Face. Some maybe you shouldn't report it to the TensorFlow, and because of the data can be potentially the data potentially the data recovered from the saved model can be potentially endangered. So it can also you need to take extra care when of the model, it can be harmful, although it didn't look like that. And if you found some endangered model, you should for example report it to TensorFlow Hub mm, or Hugging Face, not to TensorFlow itself or PyTorch. And here are some of the safety rules you should follow as suggested by the developers. For TensorFlow, um, you should assume that TensorFlow program can execute almost every code, and it is Turing complete, and it is right now they claim that for the format of PNG and BMP and anything like that, it will be trusted, but other inputs should be run in the sandbox. And the TensorFlow claims that in the eager mode, the shape inference function are escaped. So that means that in the eager mode is much more easy prone to attack. And PyTorch, they warn us we shouldn't use torch load on with weights only false on the untrusted model checkpoints, and they recommended us to use safe Kansas. And they also proposed several security guidelines for the CDCI of developers, which is very interesting, such as they try to protect um, merge both credentials from leaking. And for the paddle, it's just another different library, and it's similar to Tesla.